In this video, we'll look at some of the most basic methods of control. Later on, we'll add options like integral and derivative. But to start out, we'll start with just on-off control, adding hysteresis, proportional control, and then try to understand the relationship between the proportional band and gain, which are just inverses of each other. It's easy to use a heating system that controls temperature as an example. That's an easy one to picture mentally, I think. But these control methods apply to any closed loop system. Another one we might reference is like a servo motor positioning system. That's another one easy to sort of picture mentally. On-off control is the most basic method. It's very simple. It can work, especially if the system is more of a slow responding system, perhaps with significant mass and accompanying inertia. This might work. Or if you're just looking for the most basic way to control something. So let's do an example. If you have a slow responding system with that mass and inertia, let's pick a heating system. You might have a set point, which is your temperature that you want to maintain. If your system is below temperature, below the set point, then this control method will call for heat. It'll be on. It'll turn the system on, and it'll start heating. So let's say you're down here, and then here comes the heat, and it's rising, rising, rising. As soon as you hit and go over the set point, it'll turn off, but the thermal mass of the system might keep it going a little bit, and then it's going to start to cool down. As soon as you get to the set point and go under the set point, this type of control would be comparing that to feedback to the set point and say, okay, turn off the heating element. And of course, the thermal mass and the inertia would carry it maybe under a little bit. It's did I say turn off? It'll turn on. I don't remember which I said, but it'll turn on. But the thing it'll take a little while to reverse the direction of this heavier thermal mass, so that you get this kind of oscillation back and forth. Again, right now it's off. The heating element's off, and now it's cooling down. Okay, turn back on. It'll turn on. Of course, it takes a little time to get that thermal mass going in the other direction. Now it's heating back up, and so on. So this is sort of, and this type of basic control is on-off control. Like I say, it can work. It's for some systems. For fast responding systems, simple on-off control can be problematic. Let's show you maybe how that might play out. So let's say we can use the heating system again, but let's say it's a really quick response. So your system is under temperature and you're calling for heat. It's on, you're down here. You go to the set point, and as soon as you go over, you'll turn off, and it's very quick to respond. Whoop, now you go under, and it turns on, turns off, turns on, turns off, turns on, turns off, turns on, turns off, turns on, turns off. Very rapid oscillation. That's going to wear out components. It's just going to be a rapid amount of oscillation, a lot of noise. The switching components could wear out. So yeah, it's a very noisy and stressful type operation. Just as a side note, if this was a servo motor positioning system and the set point was actually a set position that you want it to go to, there will be some of this at a very microscopic level. The servo motor, if it goes past the position, it calls to reverse direction to get back to position. And then if it goes past the position in the other direction, again, it'll reverse. So it's constantly shimmying back and forth. There is that attribute of a servo motor where it's constantly sort of a little bit of vibration as it holds its position. Also, by the way, stepper motors can avoid that vibration. They're not constantly adjusting to hold their position like a servo motor. They can hold their position just with a fixed magnetic field. They have a different mechanism that they're using. Also, as I've brought up, heating system and then maybe a motion control system, you can see these examples apply, but you have to sort of think of what's happening, and there's different things happening. Like a set point for the heating system is a set temperature, and if you go over the set point, the heating element turns off, or if you go under, it turns back on, perhaps. With servo systems, I think you can see if you go past the position, it doesn't just turn off. The signal actually just has to reverse direction. So you'd have a sort of a reverse of the motor back to find it, and then if it goes past the position in the other direction, of course you have to reverse direction again. So it's more of a polarity reversal on either side of a set point that's a positional set point. So let's keep thinking in terms of our temperature controlling system, and let's solve this problem. If it's a fast response or fairly fast, I mean, that's relative term. So, but if we want to avoid this rapid oscillation about the set point, which is what you would get in this case, if you remember, if it's fairly quick to respond to temperature, you can add hysteresis. So you'd have on and off control with hysteresis. Hysteresis also may be known as deadband. And what we're going to do, okay, thank you, Dell. If you saw that ad pop up, probably you did. Don't call me, I'll call you. All right, so with hysteresis, what you're doing is you're going to add, instead of a single set point, you're going to add an upper threshold point and a lower threshold point, or you could call it an upper trigger point and a lower trigger point. And what's going to happen, let's take our temperature signal again and watch what can happen. So if you're starting off with a cold system, we'll say down here, I guess. So here's your temperature and it's rising. The heating element is on, the system's cold, and so you're trying to, it's trying to bring it up to the set point. So here's your temperature of your system, and it's rising, rising, rising. Now, I got to the set point, and I went past the set point. It's not going to turn off. The heating element's going to keep going until you get to the upper threshold that you set. Now it's going to turn off. And the temperature will start to fall down. And here the temperature falls below the set point, but the system will not turn off the heating element. It'll just keep going until it gets below the lower threshold. Now it'll turn off and it'll reverse direction, start to heat again. So it's calling for heat, still calling for heat, even though I went past the set point. Okay, now it's turning off. Okay, and now it's falling. It's not going to turn on yet. It went below the set point, I know, but it's not going to turn off. I mean, turn back on until you go below the lower threshold. Okay, now it's turning back on. Heating, 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 cooling, 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 even below the set point. Okay. Yep. So you've solved this rapid oscillation problem about a single set point by adding deadband or hysteresis. Of course, you have to be able to live with or tolerate the fact that your temperature isn't going to be right on the set point. It's going to be within a few degrees of the set point, or some amount of degrees, whatever your hysteresis that you've added. So you have to be able to tolerate that in your system. And that's the trade-off, really. I mean, you're gonna solve this rapid oscillation that can wear parts out. Yes, you're slowing it down. The system's going to have a slowed down response now, but you've done that at the cost of staying tight to the set point, however many degrees you wanted to add in either direction. So this temperature method can hold the temperature to the set point plus or minus a certain amount of degrees. So on-off control for a system is very simple, very basic, easy to implement. If you want to get a little more sophisticated, or you can head to proportional control. With proportional control, you're going to have your set point, but then you're also going to have what's called the proportional band, or PB. So let's put some maybe actual numbers. We'll pick some easy numbers to track in our heads, and then run an example of what happens with proportional control. So for this example, we can have a set point of 100 degrees, call it Celsius if you want, and a proportional band of 10 degrees. Here's the proportional band. It's the band that's the set point would be the center of the band. So the proportional band is 10 degrees. Proportional band is also sometimes specified as a percent of the range. So if we make up a range in our head, we could say the system has a range of maybe 0 to 200 degrees. Then we could also say that the proportional band is 5%. 5% of 200 would be 10 degrees. So either way, you can specify a proportional band in terms of the actual range of degrees, or what percent of the range of the system. So let's try to run an example and try to see what happens with a proportional control system. Again, let's use the heater starting out cold. The system's cold. It's calling for heat, and so it's bringing the temperature up. And now we're just approaching the bottom part of the proportional band. As soon as you enter the proportional band, something's going to happen. We look over here for our heater example. The control signal that the controller is going to send to the system as far as what to do is going to be a little more elaborate with proportional control. As soon as the temperature of the system gets into the proportional band, you'll see we've been perhaps running that heating element at 100% power. And now it's going to start throttling back. So this is our process variable, the temperature of the system, and it's been rising with 100% power applied to the heating element. And now we're getting into the proportional band. And as soon as we do that, it's going to start throttling back. The controller, with its control signal, is going to communicate that to the device that's controlling the amount of power given to the heating element. So it's going to start throttling back. The control signal from the controller could be a 4 to 20 milliamp signal, for example. It could also be pulse width modulation, that starts in this area. We'd be at 100% duty cycle, and then it's maybe going to go down to all the way down to 0%, and that might be a good one to have in our minds. Let's say this 100% and 0% could refer to the duty cycle that the controller is applying to the control element. The control element could be a solid state relay, for example. So back to our live example, we said maybe 100% power applied, then we hit the proportional band, and with proportional control, the control signal is going to start dialing back. So we're back, and it's applying less and less power to the heating element. And here we might be at like 50% power. And that's the set point we want. If we go over, you can see now we're going to have less than 50%. It's going to start applying less and less power to try to bring it back. Okay, and it might do something like this. Who knows? You might be thinking, and you'd be thinking correctly, are we just going to be lucky that 50% power maintains the set point that we want? And that's kind of another topic for another day. But I mean, yes, you're right to think that it wouldn't necessarily be that the system will just luckily have 50% power applied, give you the set point that you were looking for. So there is also built in a lot of times to this ability to shift the center of the proportional band. Like I said, might have to get into that on another session. But for this session, we'll just try to get these basic concepts in place and then show you, yes, they get tweaked. There's more to add to the story. But if you can understand for now that when you enter the proportional band, it will start to reduce the power in our example. So it starts to dial back, throttle back, slow down. Maybe I could have showed that a little better. And then maybe it'll overshoot a little bit, but the thing that's going to help it come back is as you go into this part of the proportional band, the throttling back continues to decrease all the way down to 0%. So the most you would probably overshoot is up in around here. And then with this proportional control, you're going like this, and again, you're going to now, you're a little under the set point, so the power is going to be increasing. Do you see that? If you're at 50% here, if you start to dip under the set point, more power will be applied. Okay, and that's going to start to bring you back to the set point. If you go over the set point, less power is applied and start to bring you back to the set point. And if you go under the set point, more power again, and so on. And it will tend to settle in, although, yeah, we'll talk about this at a later session too. And this actually brings up lots of topics in chapter 17, which are all about tuning a process that's using proportional control, and other things we'll add to it later, like integral and derivative. But proportional control can be used by itself. It's a simpler system to do that. And notice, though, it is an improvement over on-off control. I mean, it's not just overshooting up to here, then turning off, then turning back on and off. It's actually doing more sophistication than that. It's sort of throttling back as you approach the set point. And then if you go over the set point, it continues to decrease and so on. And so you have more of a, not just full on, full off, but you have varying amounts of on and varying amounts of off, kind of, so to speak. And that all comes from the fact that when you enter the proportional band, the control signal is proportional to where you are in relation to the set point. And in contrast, the on-off control is simply has a control signal that's just on or off, depending whether you're above and below a set point, as in the very basic on-off control, or with hysteresis, it's just on or off based on whether you're above or below the outside thresholds. I've also included an example of what this might look like if it's maybe a servo motor trying to get to this position point. I don't know that it would be this kind of a 100 to 0%. It would be more of a, like we said before, if you go past the set point, it's going to have to reverse the polarity on that motor, reverse the direction. So if you go past where you wanted to go, it'll have to reverse it by a certain amount. If you go past where you wanted to be by a lot, you could, if you overshoot that much, it's going to put 100% of reverse power to the motor and try to get it back there. Of course, as you get close to where you want to be, the applied power to the motor would decrease, so that you kind of come in for a landing on your set point. And proportional control just always reminds me of anything. Take like a vehicle. How do you get to where you want to be fast? Well, you go maybe full speed until you start getting close to where you want to be. And if you were running to the grocery store in your car, you're not going to go 60 miles an hour right up to the door or right up to the parking space, right? So, you're going to, as you get closer, you're going to slow down, make the turn, slow down even more, and slow down even more, and just nicely come into your parking space, for example. It's just one that came to mind. But you can take any, sort of example like that. You're obviously not going to just go full speed and then try to jam on the brakes and come right to where you want to be. It's not going to happen. You're going to overshoot and not come into the set point, the place you want to be. And a lot of times the way you might tune a proportional control system is I'll show you an example. If you really don't or want or can't tolerate overshoot like this, which is sometimes the case, you just want to, you can bring it up more slowly, gradually. So your temperature could again accelerate at the 100% maybe. And you could try to use a wider proportional band, and just if you can imagine, maybe your proportional band would start sooner, and you might do so. So with PB or proportional band being greater, it might start decelerating here, and it might be really just slow, and very slowly come in and approach the set point. Maybe a plane approaching the runway is a better example than my goofy grocery store example. And this example, you would call this a different tuning. Notice I increased the proportional band maybe to something like 20. If you can picture, the proportional band was from here to here, and I sort of said, let's start decelerating sooner so that we don't overshoot. And so the proportional band, conceivably, I might have changed that to 20, 110 and 90, it'd be 20 degrees. Or if you remember, if we said that our system had a range of 0 to 200, perhaps I increased the proportional band from 5% when it was 10 degrees to 10%. 10% of the range is another way to specify proportional band. So I doubled the proportional band. In another session, I'll tell you that's the same thing as cutting the gain in half. So if you have a controller that has a gain setting, it's the same thing. It's just they're inverses of each other. But proportional band and gain are basically just inverses of each other. So here I doubled the proportional band, and I got this kind of result. Or I cut the gain in half would be another way you could say it. I do have a session, I'll do a video on that makes that clear, the relationship between proportional band and gain, helps define gain. I think you can see that for the proportional band of 10, our original example, we have the the 100% power applied that reduces to 50%. So you really have that spread out over 5 degrees, right? 95 to 100. So what do you have? You have a change of 50% in the control signal spread out over a change of 5 degrees. And what that means is for every degree, that you're away from the set point, what would you have? 5 degrees and 50% spread out over 5 degrees. So it seems like 10% change in the control signal for every degree that you are away from the set point. It gives you some kind of notion of this gain, what gain's all about. It's 1 degree causes a 10% change in the control signal. And compare that to what happens when I widen the proportional band. I still will have that same 100% to 50% change in the control signal, but it'll be spread out over maybe 10 degrees. If you're just looking at this section of the proportional band, I would have 90 degrees where it would start at 100 to change from 100%. It would start to throttle back from 100% to 50%, but over a span of 10 degrees. So we still have a change in the control signal of 50%. From 100 to 50 would be a 50% change spread out over 10 degrees. So now each degree is will only cause a 5% change in the control signal. So the gain's half. It's cut in half. 1 degree used to cause a 10% change in the control signal. Now 1 degree, each degree only causes a 5% change. So the gain's cut in half. Why? Well, because the proportional band was doubled, the gain goes in half. And vice versa. If I cut the gain in half, it's a way of doubling the proportional band, depending which one your controller has for you to set. It's like resistance and conductance. If you specify one, you've specified the other. If you talk about one, you've also described the other. Often, if you're trying to tune in a system that uses just proportional control, you do try to avoid the oscillation, and what you want is maybe you increase the proportional band until you see the oscillation go away. Yes, it'll take longer to get to the set point, but in a lot of processes that use this, overshoot is a bad thing. So you're trying to prevent that. So you would just keep going up. So you increase the proportional band, or you decrease the gain, either way. And you're going to come into a process that gets towards the set point like this. One thing to mention, though, is with just proportional control, tuned to not overshoot, you will always have what's known as sag. There's going to be a steady state error, meaning you're never going to get to the set point exactly. And the reason is, to avoid overshoot, you're going to be throttling back like a plane coming in for a landing. And maybe unlike the plane coming in for a landing, it's never going to get to the runway. And the reason is your system, it's going to reach a point where the proportional band causes the decrease in the control signal to the point where it just doesn't have enough to get all the way there. That's the trade-off between having enough to get there, but then the inertia will cause overshoot. The inertia in the system would cause overshoot. So if you don't want any overshoot, you have to settle for what's known as sag, or you won't quite be able to get to the set point. and later we'll talk about the solution to that, is to add integral to proportional control, and then you have proportional integral control. And the integral that you're adding is simply a way that an element in the system that's watching that steady state error. And as that little bit of offset is seen over time, it will correct it. It'll see that it's there, it's still there, it's still there, it's still there, and it'll integrate that and pay attention to it. It'll become significant over time, and it'll give a little boost and get you right up to the set point. So that's what you add to proportional control. You would add integral control and get rid of the steady state error that you have when you just have proportional control. But that's another topic that we'll get to. Also to mention, with the servo example that I have here, you can see the control signal on either side of the proportional band. On the one hand, if you're trying to get to the set point, the position that you want, you'd be applying 100%, and then it would go to 0. When the motor arrives at where it should be, you want to apply 0 power to it. So this would not be the 50% that we were using for the heater. It would be 0% applied to the motor. And if you go past, you'd have to start applying power in the opposite polarity, which is why I have a negative 100%. And you can see how the proportional control works well to bring a servo motor to position. If it overshoots a lot, it'll be hit with a lot of power to bring it back quickly. If it undershoots a lot, it'll bring back quickly. And so, for a servo motor, your proportional band, the middle of your proportional band, would associate with a control signal of 0, calling for nothing to be applied to the motor, because you're there. You want to be there. And then you have opposite polarities on either side of the center of the proportional band. So it's very different, than with a heating element. You don't apply 0 power when you get the temperature where you want. You just want it to hold that heat. So with heating systems, the center of the proportional band might be lined up with 50%, or you oftentimes have to be able to have that flexibility. The control signal, maybe it's 30% at the center of the proportional band that holds you at the set point that you want. And so there's a little more to think about, with some systems that when you get where you want to be, you need to hold that amount of power that you're applying, as opposed to maybe a servo motor where you don't want to apply power, you don't want it to move at all. You got it right where you want it. So they're very different, and that's maybe just a good thing to keep in mind, that the systems themselves can be different. So you have to adapt this proportional control methods to what system you have to be thinking, what your system looks like. Also, with the servo motor example in our heads, it brings up another type of action that we'll need, and we'll talk about that later too, and that would be derivative action, which really helps a motor if you're coming flying into your set position as fast as you can, and you don't want it to overshoot. That's pretty hard to do with just proportional control. So derivative control would see a sharp overshoot and pull it back quickly. It also gets it started quickly from the mass of the robotic system that has to get moving, its own inertia. So derivative action will also say, I saw a command to get to here and nothing moved yet. So it would give it a little boost action to get it there faster, and then to keep it from overshooting. As soon as it sees it go past the set point, derivative action also will kind of yank back on it quickly with a braking action. And so when you have something fast moving like a servo motor, but also you want it to come flying into its set point as quickly and then slow down as quickly, and so on. So you get this boost in braking action from derivative control. For things like servo motors, it's more necessary. And again, you have to think about what your system requirements are, as opposed to what kinds of control methods you use. So Chapter 4 does introduce all of this. It starts with on-off control, adds hysteresis, does proportional control. It does introduce those concepts of integral and derivative, what they are, at least defines them. Later on then in Chapter 17, you get more details. We'll look at how do you tune a process, what do you use for which processes, and so on. With proportional, integral, and derivative, you have what's known as PID control. And I think I'll just wrap up this video. It's getting long. Maybe just sum it up. If you remember, we had mentioned PID control started with, I think, the Navy wanting to have a ship, that could be on autopilot. So simply a mathematician observer sat next to the person steering the ship and observed what was needed to counter different situations. So, if you have a new heading, a new direction you want the ship to go, he would notice, the rudder turned, full lock, 100% to get it going. But as the ship starts to, turn, starts to spin around, as it starts to approach the direction that you want to be going, you're going to not go with full rudder. You're going to start to back off the steering wheel, right? Same in a car, and so you're going to ease into your new position. You're not going to go full lock, and as soon as you get there, go back, because your car will overshoot, or your ship would. So he observes that. So that would be the proportional part. As you get close to where you want the direction you want to be pointing, you start backing off the rudder. Now you can hold that rudder position, but there might be some offsets, such as a current that's steady, pushing the ship a little off course. So what are you going to do? You're going to add a little more rudder, a little more steering wheel action towards the direction you want to go, to counter that steady state current or air that's impacting the direction you're going. So now you have that. That would be integral control. And then to counter things like a sudden disturbance, like a wave might come. So if you see a wave coming, as soon as a wave hits the ship, it would knock you off course. But again, the person steering the ship would just give a quick twist of the steering wheel, the rudder, to counter that sudden impact of the wave and stay on course. So that would be derivative action, that quick action, responding to a quick disturbance, a sudden change in the air signal, really. It's responding to quick changes in the air signal. So a sudden impact of a wave, you'd have a sharp rise in the air signal suddenly, and that slope of change, that rate of change, it happened very fast, because it was, that's the derivative that's going to call for a quick response to counter that. So a quick change in air signal can be met with a quick response if you're using derivative, and a steady state air in the air signal that's just there, maybe like in the ship example from a current, that can be countered with just integral action. You're just watching it over time, and it becomes significant over time. So, and there's many examples you can pull from, driving your car down the highway, a gust of wind, and if it's a windy day, and you might give a quick twist at the steering wheel to keep your car from moving off track very much from that gust of wind. So that would be derivative action, and so on. So this video turned out longer than I thought, so I will stop here, and I will actually put a second part 2 video together that has some actual examples, some real world examples, some numbers, some charts and stuff that help also bring these concepts into focus.